Hey, what's up guys? Welcome to another video on low power design. In the last video I showed you how to use a very simple latch circuit to completely kill power to the Arduino. In this video we're going to leave the power on, but instead configure the Arduino to enter a very deep sleep state, and then of course we'll wake it up with a digital input or a timeout from the internal Watchdog Timer. So this is where things get pretty cool, and don't worry, we're not going to be using any libraries or anything like that. We're going to do all of this from scratch. So let's take a closer look at what I got going on over here. Okay, so here's the Arduino. It's just a bare bones standalone Arduino on a breadboard here. We're using the ATmega 328P-PU. And this is running at 16 megahertz with a 5 volt input. And in another video we'll talk about lowering that voltage and the frequency to reduce the power consumption even further. The code running right now is just baseline code here to see what the current consumption is, just running full tilt. So we've got an LED hooked up to digital pin 4. We set that up as an output, and then we're just blinking that. And if you look up at the meter here, when the LED is off, you can see we're at like 17 milliamps or so, closer to 18. And then when it turns on, it kicks up to 20 milliamps. So one of the things that the datasheet talks about is to write all of your digital pins either high or low when they're not used. So let's go ahead and test that out. Okay, so basically what I did here is just loop through all of the I/O pins, and I'm just setting them all as outputs. Okay, so pretty simple stuff here. You do want to watch, if you're going to do this, if you have some other device hooked up to those pins. So you want to make sure they're driven either way. They don't all have to be driven low. They just need to be driven one way or the other. You could even, if you don't do this, you could also just bias them with a pull-up or pull-down resistor, and that'll do the same thing. And surprisingly, this does save quite a bit of current. So if we look at the meter now running, when it's off, we just went from 17 to 18 milliamps now down to about 13 milliamps. So I just wanted to throw that one in there because it's just something so easy that you can just basically just write that little piece of code and you can save a few milliamps. And every milliamp counts when you're talking battery applications. So there's that. Now let's get into actually putting the Arduino to sleep. Okay, so let's first go over to the datasheet, and they do a pretty good job of explaining the different sleep modes. And the one we want to try out is the powered down sleep mode, and this is the deepest sleep you can put the Arduino into. And you can see here from this table all the things it shuts down and the different ways you can wake it up. So if we go down, we want to see how you actually put this to sleep. And I'm going to keep scrolling down. And here is the sleep mode control register. So we need to first set this up. And we're going to set up the power down mode here. So it's pretty simple. You just need to make sure that the SM1 bit here is set. And then there's also this SE bit there, which is the sleep enable bit. So it says that it's recommended to write the sleep enable bit to 1 just before the execution of the sleep instruction. So what is the sleep instruction? Okay, so just a few sections up, they give you a little example here of the how to implement the sleep instruction. And here you see the assembly code example. And I've done this in other videos, but what we're going to do is use inline assembler in our Arduino code to execute this instruction. So let's go back now to the code, and you can see here what we're going to do is go to sleep right after we turn that LED off. So the first thing we do is set that power down mode. Remember, the SM1 bit needs to go high, so we just take a 1, shift it over 2 places to that part of the register, and then do an OR equal. So that's a nice clean way of setting only that single bit in that register. And then we're going to go ahead and enable sleep, which is only that first bit, so just an OR equal on that first bit. And then this is how you do the inline assembler to execute that sleep instruction. And again, you might remember seeing this from some of my other videos. So I've got this code running now, and you can see here that actually I'm going to just cycle power there. Okay, so the LED turns on, and then it goes into the low power state. And you can see that we're getting about 381 microamps, so 0.381 milliamps. So that's pretty good. That's less than a milliamp. But we can do much better than that. So let's keep moving on. And of course, right now there's no way to wake it up. We don't have any interrupts set up. We're not running the Watchdog Timer. So we'll talk about that in a little bit here. But let's see how deep of a sleep we can get this into. Okay, so the datasheet talks about different ways that you can reduce power consumption, and one of the big ones is to turn off the analog to digital converter. So we do that by going to the ADC control and status register A here, and we just want to flip the bit here for the ADC enable, so bit 7 of that register. So we just want to write a 0 to that bit, and that will kill the ADC. So let's go ahead and do that. So you can see here we've got the ADC SRA, and we're going to do an AND equal now with the inverted bit. When we shift over 1 to the 7th place, we're going to invert that, make it a 0. Everybody else is a 1, and that's a nice clean way to clear bits out of a register. And I did not preload this one, so I have to program that real quick. Okay, so I'm going to go ahead and power it up and watch the meter here. So now we're at powered up, and now when it powers down, goes into that sleep state. We went from about 380 microamps now to 58 microamps. So that's a huge increase. So that alone, I mean, now we're in good solid battery territory now with this setup. But believe it or not, we can do even better than that. So let's try the next one. Okay, so the next thing we're going to try out that the datasheet talks about to reduce power consumption is to disable the brownout detection unit while sleeping. So to do this, we scroll down to this MCU control register. And this is kind of tricky, actually. It took me a couple tries to get this to work because it's a timed sequence. And if you read this, it's a little convoluted. You know, it's talking about, you know, to turn off BOD during sleep. Writing to the BODS bit is controlled by a time sequence. To disable it, you need both BODS and BODSE must first be written to 1. So you can see it's kind of confusing. And then to set it, you have to, the BODS bit has to be set to 1, and BODSE must be set to 0 within 4 clock cycles. And then to make matters worse, it also says that the sleep instruction must be executed while BODS is active in order to turn it off. And okay, so anyway, and of course it is automatically cleared after 3 clock cycles. So this is all of this has to be done in order. In fact, I tried it several different ways and it didn't work, but this way, that I'm about to show you, actually does work. So let me show you how I did that. So right here, so I moved up the sleep mode and sleep enable stuff up here, and right here is the brownout detection disable code right here. So what we're going to do is first set both the BODS and BODSE bits at the same time. So I'm just going to shift a 3 over to the left 5 places and order that with the MCU CR register. So basically what I'm doing is setting both of these bits here. So I'm taking a 3, which is, you know, both of the, you know, 2 bits set, shifting it over 5 places so it would set both of these bits here. That's the first thing I'm doing. And then the second part here, which is the tricky one, is we need to do both a set of the BODS bit and a clear of the BODSE bit, okay? So the way I'm doing that is taking the MCU CR register and making that equal to the MCU CR register, just taking it back in and clearing the 5th bit, which is the BODSE bit, here, the 5th one here, and then ORing that with the 6th bit, which is the BOD S bit here. Okay, I know this all sounds pretty confusing, but we're basically just setting this bit, clearing that bit. So the order is set both of the bits, then set this bit again, and clear this bit at the same time. Okay, and that's all there is to it. And I've got this code running. Take a look up at the meter. Let's do a power cycle here real quick so you can watch it. Okay, LED kicks on, then sleep mode. Wait a minute, did we lose power? No, we didn't lose power. It's just that low. It's incredible. Look at that. We are now running at 0.328 microamps. So remember when I thought that 0.338 milliamps was good? Well, this is really good. This is the ultimate deep sleep. Okay, so I think we can stop there. There may be a few other things we can do to reduce that even further, but I'm happy with 0.328 microamps. So now let's talk about how to wake it up from this deep sleep. Okay, so this deep sleep state can be woken up by any digital input that's hooked up to an interrupt. So what I did here is hooked up a push button to digital pin 3 on here, which is interrupt 0, and I've got a pull-up resistor, little 10K there, hooked up to the 5 volts to that pin. So I've got a pull-up resistor, and then on the other side of that push button, we're going right to ground. So it's going to be a falling edge interrupt. And then over on the code side here, I've just attached an interrupt to interrupt 0, which is digital pin, digital pin 2. Sorry, I said digital pin 3. It's digital pin 2. So I hooked that up. The function we're going to call is just digital interrupt, and it is going to be a falling interrupt. And so I added in the function down here, void digital interrupt. And the other thing we did here is when I looped through all of those pins, now I don't want to set that interrupt pin as an output because now it's acting like an input. So if it's not equal to 2, then this is kind of a clumsy way of doing that, but it's okay for this test here. So I've got that code running over here now, and so we're in this deep sleep state. You can see up there that our current is very low, and when I press the button, it wakes it up. Okay, so it's as simple as that. Wakes it up, the LED turns on, and then it goes back into its deep sleep state. Okay, so now let's get into some cool stuff. Let's implement the Watchdog Timer. Okay, so let's talk about how to implement the Watchdog Timer. And this is pretty cool. This is a timer that runs on the part completely independent from the 16 megahertz clock. Okay, so this is something running internally to the part. So let's scroll down to the Watchdog Timer control register here. And if you go down a little bit, you can see the various modes, and here is a table showing the times that this can run at. And it's not very accurate, so if you need a very accurate specific time interval that you need to wake up to, you may want to implement an external real-time clock, which we may talk about in a future video. But for now, the max time we can set this to is 8 seconds, and to do that you set the WD P0 and the WD P3 bit of that register. And of course, if you need anything longer than 8 seconds, which I'll show you in a little bit here, you just have to re-execute the sleep instruction. And of course it does wake up for that brief period of time, but it's hardly anything to wake up and then throw it back into sleep. So you can get longer sleep times out of using the Watchdog Timer. So let's go up here. The funny thing about this is, again, it's a timed sequence, and this took me a few tries to get right as well. So you can see the prescaler bits here, the WD P0, P1, P2, and then P3 is all the way up here. But to change those, we need to first set the Watchdog change enable bit. Now, I found something kind of weird in this data sheet, And if we go up here, I'm just scrolling up here. It's another timed sequence setting here. So if you go up here to where they talk about how the Watchdog Timer works, they talk about this timed sequence here. So I'm actually following it this way. Write a logic 1 to the change enable bit and WDE, okay, at the same time. And then it says a logic 1 must be written to the WDE bit regardless of the previous value of the WDE bit. And then within 4 clock cycles, then you can change the WD and watch scaler bits. Okay, and we'll talk about that here in a sec. I know this is all confusing, but I wanted to show you that in the data sheet as to the reason why we do it this way. So basically what we need to do is first flip the bit, the change enable bit, and then we can set up the Watchdog Timer configuration, which needs to be in interrupt mode. So we need to make sure that the WDE bit is cleared and the WDIE bit is set. Okay? And we're going to, like I said before, we're going to run this at an 8-second interval. So let's go over to the code here. Here it is right up here. And the first thing I do is set the entire register to 24, which is just setting these 2 bits, the change enable and the WDE bit. And then right after that, I'm setting just the prescalers only. So that's just the WD-P3 bit and the WD-P0 bit. So that sets it to 8 seconds. And it's also clearing the WDE bit and the WD-CE bit. Okay, I know this is getting crazy. Okay, so we set that up. And then finally, I just only set the WDIE bit, okay, which sets it up in interrupt mode. And you don't have to do this every single time. We can put this up at the setup as well, and we can put a lot of this actually in the setup, and maybe we'll do that here towards the end. But anyway, that's it. So now we've got the code running here. I'm gonna do a power cycle. Okay, so the LED turns on, turns off for 8 seconds. Okay, and we can time that out. And then the LED should turn back on. There we go. So we know that it is actually running. And we still have that digital input running as well. So we can still wake it up. And that doesn't affect the Watchdog time either. So as soon as I hit that button, it wakes it up. It goes back into its deep sleep for 8 seconds. And then up at the meter here, we are no longer pulling 0.3 microamps. Now we're pulling about 6 microamps. So the Watchdog does use some current. I'm going to wait for it to go back into its sleep so we can zoom in a little bit on that. Oops. Okay, so it's about 7 microamps. Okay, so that's pretty good. So that is the Watchdog Timer running.
Terrible. Shocking. $10. Here it is under the microscope. Shockingly bad.
Okay, so I said that we can extend that Watchdog timeout by simply executing that instruction, the sleep instruction, twice. And basically that's what I've got here in the code. I've moved all of the setup stuff up in the void setup function up here. So we got the Watchdog stuff up there. We disable the analog to digital converter up there. And we set up the sleep register up there as well. Again, don't forget to re-enable your analog to digital converter if you are using that in your project. So you want to do that after you wake up. But down here, what we've got is the loop here, and I'm just looping through that twice now. You still have to set up the brownout detection disable registers here, so where you're actually going through and disabling that. And then we execute the sleep instructions. So now, over here, we should get double the time, and I've been running this here for a little bit. And the funny thing is that up on the meter, you don't actually even see the little blip the increase in current when it wakes back up and sets up these these registers. So that's how fast it is able to re-execute those instructions to change those registers and then execute the sleep instruction. So let's just go ahead and check this out here with a stopwatch. So we're going to power up, and then as soon as the LED turns off, we start it, and we'll see and make sure that we do get the 16-second Watchdog timeout. So right now we are running at about 7 microamps. All is good. Didn't see a blip up on the meter, and there you have it. So it was a little bit before 16 seconds, but again, it's not going to be that accurate. But I did want to show you that you were able to get about you can double your time or triple your time or whatever. You can put anything you want in this for loop. So that's pretty much it. There is one other thing we can look at, but I might bring that up in another video, and that is the power reduction register, and they talk about that in the data sheet a little bit, and I probably passed it up, but that basically allows you to disable various peripherals on the part while running. I didn't talk about that in this video because that's more of a up here it is, power reduction register, and this allows you to disable various peripherals in the part. So the reason I didn't bring this one up is because a lot of this stuff, if you disable it, you're going to break things in the Arduino. So like you can't disable timer 0 because you're using timer 0 for your delays. And then other timers control the PWM outputs and things like that. And of course, the USART 0 there, which is your serial port. So you can use it. You just put PRR and you set all these to 1s, and that disables them. And that will save you some, reduce your current consumption. And I did test that out. It's pretty easy. This does nothing for you in a sleep state, though, because when you go into that deep sleep state, you already are disabling all of this stuff. So this is more of a runtime while you're running type savings. And I was able to get it down to about 10 milliamps running with disabling everything in here, besides timer 0 because I was using delays. Oh, and that does bring me to one other point here. So we have this little delay here, this 1 second delay. You could actually reconfigure your Watchdog prescalers to 1 second and then just enable sleep mode there to save even further. So if you're really tight on your battery supply, you could always implement implement a Watchdog timeout for every one of your delays. So that's just another implementation you can use. So anyway, I'm going to make all of this code available. Oh, you know what? I forgot one thing. Don't forget the ISR Watchdog Timer vector interrupt down here, okay? You need that for the Watchdog timer to work, okay? This is the interrupt that is called when it wakes up, okay? And I'm not putting any code or anything in there, but you do need this because this is called when it wakes up. I can't believe I've almost forgot that. But I'm going to make all of this code available in the description below. I may actually add a little bit more comments to it, but you can pick and choose anything out of here you want to use. Notice that we didn't include any libraries or any of that crap, so this is ready to go out of the box for you to use. And that is how to get the Arduino into a deep sleep state and wake it up with digital inputs and the Watchdog timer. Hopefully that helps. Thanks for watching.